Okay, right. So I just want to bring you to this example from our book there, from the same section. It's question 10, okay? And it's a graph of the function fx is equal to the inverse sine of 3x minus 1. And the graph is being shown here in red, and it's the graph between 0 and 2/3, right? So you can see it goes from 0 here on the x up to 2/3 on the x. And it's also saying that x is an element of the real. Okay, so we have to find the derivative of fx and then find the equation of the tangent. Okay, so it's the same type of thing we've been doing today. So we have the original function written here. I've highlighted in blue there the sub-function that I'm going to use for the chain rule. I also gave you the formula here from the log tables, okay? This is the inverse sine of x over a will differentiate into 1 over the a squared minus x squared. So this is in the logbook, okay? This portion here, okay? Right, so we differentiate that and we can see that our a value is going to be 1 and our x value is going to be 3x minus 1, and we're using the chain rule here as we do that, okay? So hopefully you can see that that's 1 over the square root of 1 minus 3x minus 1 to be squared by the diff of what's in this brackets, which of course is 3. Okay, now then we move that along and we get 3 over the square root of 1 minus the 3x minus 1 to be squared, okay? Now at this stage then I've decided to bring this over to my rough work here to just multiply this out just to make sure that you know what's going on there, because then you have to bring it back with the minus in front of it, change the sign and everything, okay? And then obviously then we get f dash x is equal to 3 over the minus 9x squared plus the 6x, okay? All right. Now, obviously we're going to move that on now to use the equation of the tangent, okay? So the equation of the tangent is going to clearly come from using the equation of the line formula that again we were speaking about today. Y minus y1 is equal to m times x minus x1. In this question, we are being very lucky because we've been given both the x and the y. Now, if you're only given the x, you have to bring that x value back into the original function and calculate the corresponding y value. So if I've only given this x, I have to calculate this one by subbing it into the original fx so that I can get that y value. Okay. So remember here we're finding the equation, so we're trying to find the equation of the tangent, which is the blue line here. It's a tangent to the curve at this point here. Differentiation is giving us slope, so I am going to sub in the 0.1 from the x into the equation I got for the differential, so that's the rate of change equation. I'm subbing in the 0.1 in there. That's what I've done in this step. Put it into my calculator and I got 4.2 as the answer, and hopefully that's right. Again, right answers are less important than correct method. Okay, then I take both those coordinates of the point down as x1 and y1 with the 4.2, which is the slope, and I'm subbing all of that in here. Now, there isn't probably an awful lot more you can do with it, right? And sometimes we leave it in that format, and that's absolutely fine, I think, as an answer. Y plus 0.78 is equal to 4.2x minus 1, or we could develop it another little bit by going 0.1 of that, which is minus 0.42. Okay, and then you could bring everything to the same side, or you could do y is equal to mx plus c format. So that's 4.2x. Bring over your minus 0.78, and you could add those two together, and you'd have y is equal to 4.2x minus, just adding those, 0.42 and 0.78 gives me okay, minus 1.2. Okay, and that's your final answer there. Okay, All right. Okay, I hope that is making it a bit clearer on how to find the tangents.